complex in themselves. It's basically built around number, strings, arrays. If we look at, if you guys can still see my screen, I'm totally not sure.
You are not sharing. We can get you back up if you need it.
Yeah. Truth is, we'll be adding more schemas or more complex types. I think the native types, at least for as far as messages go, I don't think they're going to be adding. As I talked in the Google tries to make this as backwards compatible as possible. So the typing is really limited to those 3 lower bits in the key. And as of right now, there's 5 taken up, which leaves, sorry, 5, yeah, 5, which leaves 2 more types, because in 3 bits, the highest number you can represent is 0, which leads, so is 7. And there's 0 through 5 is already taken. So to handle backwards compatibility, I'm guessing the most complex, they can only add 2 more complex types, is the only thing possible, or else they will break their own backwards compatibility and probably have to generate a new type of, encoding mechanism.
Okay, awesome. Well, thanks again for giving this talk. If anybody does have any more questions, please feel free to reach out to Chris. He shared his personal contact information. He's also on the Chicago Python Slack. So next up, we're gonna have Suhas talk about hypothesis. Please give us a couple of seconds while we get Suhas all set up. Thank you.
Thanks, everybody.
All right, so next we have Suhas. Do you want to say something, Suhas, just to make sure your volume's working? I think you're muted right now.
Okay, can you hear me now?
Yeah, we can hear you now.
Okay, yeah, I had it muted. Sorry about that.
Okay, awesome. Suhas, do you want to take it away?
Yeah. Hi, everyone. I'm Suhas. I study at Illinois Tech. Yeah, I hope you're all staying safe. I'm stuck indoors preparing for coding interviews. I'm using a book to prepare. Some of you might have heard of it, Cracking the Coding Interview. It has a great selection of problems and good solutions, but test cases. You can find some on GitHub, these test cases, but there really isn't a lot. You would think the quarantine gave me enough time to write all the test cases that I wanted. It did, but I wanted to generate them because I'd almost always miss some obvious cases, and it's nice to have less work. This led me to property-based testing. I'll start with a commonly used example, reversing an array. Now, say instead of manually writing this test, going from 3 to 1 to 1 to 3, I want to generate lists of integers so I can test a broader range. There is a library to do that. We'll come to that later, but how do I test my output now? My first thought was to find a known implementation on the web and compare it to mine. But it sounds hacky and unsatisfying. Instead of this, we can test some properties of the result itself. First, is the resultant string of the same length? If so, we're probably on the right track. Second, we can use the property that reversing the reverse of a string will give us the original back. This captures the intuition behind property-based testing. It was popularized by QuickCheck, a Haskell library. Python 2 has a library called Hypothesis. Hypothesis exposes something called strategies with which you can generate characters, strings, integers, lists, or sets of integers, and many more. You can even combine them the way you like, and you can create a custom strategy. Up next, I'll show you how I generated test data for my coding problems. Okay, so the question is, determine if all characters in a string are unique. In this function, I first create a set, and for every character in the input string, I check to see if it's not in the set. If so, I'll add it to the set. If I encounter a character that is already in the set, that means we have a duplicate, and I return false, else I return true. This is a test function which tests the above code. Here I supply the isUnique function with what I already know to be strings with unique characters, and I expect the result to be true. To generate these unique characters, I use hypothesis. It provides a decorator given to which you pass a strategy. Here, we want to generate lists, and the elements of the list are characters. I've specified that I don't want to go beyond the Unicode code point 127 to stay in the ASCII range, and I've blacklisted control characters and surrogates. And I've also specified that the elements in the list should be unique. I tested strings with unique characters, and now I want to test non-unique ones. I generate the tests in a similar way, except that I don't set unique to true, and I use a filter method to weed out randomly generated lists with unique characters. I also have to change the assert statement within the test because my function should now return false. And then I run PyTest like I normally do. I ran into another problem in the book where the test case generation is a bit more involved. So given a string like this, the function should compress it to this string, repeated characters replaced with their counts. The resulting string should be smaller, so this output is invalid and it should just return the original back. Now I need to generate strings with repeated characters. First, I'll specify a strategy to generate the characters that make up the string, which are ASCII letters, and no numbers, which I've included in the blacklist. Hypothesis provides a composite strategy with which you can combine strategies. Here, total characters is a number of characters, each of which I will repeat. I'll arbitrarily determine this number by generating integers, again, using hypothesis. I'll determine the number of times to repeat each character in the exact same way, and then append it to a list. I will then return the string. Okay, so we now have the function to generate repeated characters, which we're using to test the solution to the string compression problem. Assume the compressed string function has been filled out. Also, to test this function, I wrote another one to decode the string, and I'm going to use these three functions to write my test. In the test function, I assert that the input string is equal to compressing it and then expanding it again. So compressing and expanding it should leave the string unchanged. It's similar to what we saw with reverse earlier. This encode decode pattern is pretty common. I don't know how to choose properties before I had read blog posts about it. In one of John Hughes' talks, he talks about how reducing complex data structures to simpler ones can help. I found this very helpful when trying to come up with properties to test linked list problems. Say I have to write a function to remove duplicates from an unsorted linked list. To test this function, I need to pass it a linked list first. But before that, I create an array of integers using hypothesis, convert this array into a linked list, and then pass it to my remove duplicates function. The linked list that is returned can again be converted back into an array. To test the result, I just have to check if the set created from the original list is equal to the set created from the result list. You can see how converting to an array representation can simplify things. It can simplify other problems too, like returning the kth last element from a linked list, determining if the linked list